Hey everybody, this is a lecture on the first section in chapter 6 of our elementary statistics book. In chapter 6, we're going to be focusing on normal probability distributions. And then this video is our first video from this chapter, and 6.1 is what we're focusing on here. So 6.1 is called the standard normal distribution. Okay, but we're also going to be learning quite a few other things. So we're going to start with the uniform distribution and finding the area of a rectangle, and we're going to learn about how area under a density curve is actually the same as probability, or the chance of being in that region that we're finding the area of. Okay, so in this section we're going to learn about standard normal distribution, and with the standard normal distribution the graph has to be bell-shaped, the population mean mu has to equal 0, and the standard deviation sigma has to equal 1. Okay. But like I said, we're going to start with the uniform distribution, and then later on we'll do standard normal. And I may split this up into 2 videos, but I'm just kind of this is going to be our first video. So, all right, so let's start with the uniform distribution. We've already talked about this before. So the uniform distribution is a distribution that is roughly rectangular in shape. And remember that when I keep saying distribution, that's really referring to the shape of the graph. Okay, so uniform distribution is roughly a rectangular shape. Okay, and the area under the graph of any continuous probability distribution is equal to 1. So the total area under a rectangle here is going to be 1. And then later on when we do the normal distribution, the total area under the bell curve is also going to be 1. Okay? And for the uniform distribution, one nice thing about rectangles is the area of a rectangle, as you hopefully already know, is usually written as length times width. Here they're calling it area equals height times width, but height is just another name for length. Okay, so let's see some examples of the uniform distribution, and then here's also the formal definition in case you're wondering. So a continuous random variable has a uniform distribution if its values are equally spread over the range of possible values. Now, it doesn't have to be exactly a rectangle. When we were doing histograms, we saw that it was roughly rectangular. However, here, because we're talking about a continuous random variable, remember that continuous means that we have decimals. Okay, so if we have a continuous random variable, continuous means we'll have decimals. And if we have decimals, decimal values, then there are really an infinite number of possibilities, because with a decimal you can always write out more and more digits. Okay? So the graph of a uniform distribution results in a rectangular shape. All right, so the normal distribution we will return to in more detail. But as you can see here, for a normal distribution, the graph has to be symmetric and bell-shaped, which we've already mentioned before. And the problem with it is you have this complicated formula. We're not going to be using this formula in our class. This is more of like a math major formula, whereas this isn't more of a developmental elementary statistics class. But obviously, finding the area underneath this curve is a lot more difficult for a normal distribution than finding the area underneath a rectangular or uniform distribution, which is why we're starting with uniform. Just remember, normal distribution, though, is this shape, not a rectangular shape. And I will be giving you a table A2 from our book. So later in this section, after we're done with rectangles, then we'll be moving on to how to find the area underneath a bell curve or a standard normal distribution. Okay, so rectangles. Let's jump into an example. Okay, so during certain time periods at the JFK airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed. Okay, so remember, uniformly distributed means it's a rectangle, between 0 minutes and 5 minutes, as illustrated in the figure on the next page. Okay, before we even go to the next slide, I want to point out to you that because they said it's uniformly distributed, I can actually already even draw a picture here. And the reason I want to draw the picture before we go to the next slide is when you're doing your homework, there are about 3 homework problems where they don't have a picture, they don't have a rectangle drawn for you, and they don't tell you the height. So I wanted to go ahead and show you that process here before we even go to the next slide. So let's learn how we would make a rectangle out of this. So when they say uniformly distributed between 0 minutes and 5 minutes, these numbers that they're giving us, 0 minutes is where it starts and 5 minutes is where it ends. Well, all we have to do is draw a rectangle, and we know that our rectangle starts at 0 minutes. So they're referring to the x-axis when they're giving you the 0 minutes and the 5 minutes. So you can imagine here our x-axis is going to start at 0 and it's going to end at 5. And that's supposed to be a rectangle. Obviously, I'm kind of shaky from all the coffee that I drink, but I think we get the idea. So this horizontal axis here happens to represent starting at 0 minutes and ending at 5 minutes, and then it's rectangular in shape. But we don't know the height of the rectangle yet. And this is how your homework is. They don't tell you the height of the rectangle and they don't give you a picture. But yeah, this horizontal axis here is in minutes. So then the question is, when you're doing your homework, if they don't give you the height of a rectangle, how do you figure it out? Well, it turns out that to find the height of the rectangle, you can just go ahead and use a pretty straightforward formula, which I'm going to present right now. So this here, how far up the rectangle goes on the y-axis, that's what we're referring to as the height. Okay. And remember, we need the height of the rectangle so that we can find the area of a certain region of the rectangle, because the area is going to be height times width. Okay, so it turns out that if you look at the entire rectangle, the formula for the height is given by height equals 1 over the range. Okay, and when they say the range, they actually mean the range of the entire rectangle. So in this particular example, the range is going to start at 0 and end at 5. So that's the maximum, 5, minus the minimum, which is 0. Okay, so 1 over the range is going to be the same as 1 over the maximum minus the minimum. And from our picture, we can see that the maximum is 5 and the minimum is 0. So this is going to be 1 over 5 minus 0. Okay, and 5 minus 0 is 5. So this is just 1/5. So 1 over 5. Okay, but when you're doing your homework, you are going to need to use that formula. just remember that range is the maximum minus the minimum. So 1 over the range is the same as 1 over the maximum minus the minimum. And then with this one, on a calculator or in our head, 1 over 5 is the same as 0.2. Okay? You can literally just type in 1 divided by 5 on your calculator, and that should give you 0.2. That's the decimal form. Okay, and that's the height that we just found. So they didn't even draw a picture for us, but because they said uniformly distributed, I was able to construct a rectangle that started at 0, ended at 5, and then we just found the height, which is 1 over the range, 1 over 5 minus 0, which is 1/5 or 0.2. So now we know the height of this rectangle. Okay. So here the height is 0.2. Okay, and then how do we find the width of the rectangle? I mean, they haven't asked us to find it, but as you might have guessed, you just subtract. So the width of this whole rectangle is going to be 5 minus 0. So this entire width here is 5 minus 0, which is 5. Okay, so width is basically just the same as the range. So the maximum minus the minimum. So the whole width of the rectangle here would be 5 minus 0, which is 5. Okay, but when we're actually doing a problem, the width that they ask us to do won't be the entire width of the rectangle. It'll probably be a width of some part of the rectangle. But that being said, when you're finding the width, you basically just take the right side of your rectangle and the left side of your rectangle and you subtract, and that gives you the width. Okay? Cool. So let's return to the slides. Okay, so as you can see in the book, they have constructed basically the same thing that I was just talking about. They don't explain it quite as much as I do. But they've drawn a rectangle. Here they've skipped the work that we used to find the height, but they do have the height labeled as 0.2, which is 1/5. Another important thing to note that I did not write on my graph because I didn't really have room is that the height of the graph is actually the same as a probability. Okay, so the y-axis or the height of the graph is the same as p of x, where x here is representing the waiting time in minutes. Okay, and one important point to realize here is that the total area underneath any density curve, what we've drawn here with the rectangle is called a density curve. The total area underneath any density curve has to be 1. And the reason the total area is 1 is because if you add up a bunch of smaller rectangles, those smaller rectangles, 100% of the time you're going to have to be in one of those rectangles. So the area is 1 because 100% of the time your waiting time at the airport has to be between 0 and 5. Okay, so let's return to, before we go any further in this example, I want to return to some earlier slides here. So this graph that we've constructed, which was a rectangle, is called a density curve. And this is the graph of any continuous probability distribution. Obviously, it doesn't have to be a uniform distribution. It can also be a bell curve or a normal curve. It's called a density curve, and for any density curve, it must satisfy the requirement that the total area under the curve is exactly 1. And that's true because 100% of the time, you have to be somewhere in the range of values that are given. Okay, so in other words, if you're at the airport, because the waiting times were between 0 and 5 minutes, that means that if you select any given person from that airport in the data set that we have, because they're between 0 and 5, 100% of the time, they're going to have to be some number here. Okay, so that's why the total area is 1. Remember that 1 is the decimal format of 100%. Okay, so because the total area under any density curve is equal to 1, which is 100%, there is a correspondence between area and probability. Remember, probability is the chance of something occurring. So the total area under the density curve is 1 or 100%. So referring to this figure here, if we wanted to find the probability of having a waiting time between 3 and 4 minutes, it would make sense that because that's 1/5 of this entire graph, that we would have a probability of 1/5 of being between 3 and 4 minutes. Okay, but we'll see actual examples now. So it is important to note that even though on this graph here that we've constructed, they're only labeling 0, 1, 2, 3, 4, 5. Remember that a waiting time in minutes can be measured as a decimal because it's a continuous probability distribution. So it's actually possible to have a waiting time of 1.2, 3, 4, 5, 6, 7 minutes. And you can always measure more and more decimal places, which is, remember, continuous means that you have decimals. Okay, so this x-axis is actually decimals. Okay. Now, as they point out in the book with this example, by assigning the probability of 0.2 to the height of the vertical line in the figure, the enclosed area is exactly 1. Okay, but that's just the definition of a density curve. And one easy way to check that your rectangle makes sense is just to do the height times the width. Well, if you do 0.2 times 5, 0.2 times 5 should give you 1, which is 100%. And then in general, when you're doing your homework, we should make the height of the vertical line in a uniform distribution equal to 1 over the range, as I showed in the stuff that I wrote on the board. Okay, so let's try to answer some questions about this graph. So this is an example using the same graph that we've been talking about. But now they're saying, given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So when they say at least 2 minutes, if someone says, well, we need at least 2 eggs to make an omelet, that means 2 eggs or more. So just think of it in that way. So at least 2 minutes is the same as saying 2 minutes or more. Okay, so like here, what they're asking is to find the chance that we're between 2 minutes and the maximum, which is 5 minutes. So we're trying to find the area between 2 minutes and 5 minutes. So this area here. And we know that the total area equals 1, but we just want to find this area here, given that the total area of this whole rectangle is 1. So how do we do that? Well, we already know, we've already calculated that the height is 0.2, and that's not going to change. The height is constant throughout this. So in order to answer their question, we just use the formula for the area of a rectangle. So area equals height times width. So area equals height times width, we already calculated that the height is 0.2, and then we can figure out the width by just looking at the picture. Okay, so, and subtracting. So if we look at the picture here, the width is going to be, well, the maximum is 5, and then the minimum of the rectangle that we're trying to find the area of is 2. So here the width is going to be 5 minus 2, which is 3. So width equals 5 minus 2, which is 3. Okay, so area is going to be height times width, which is 0.2 times 3. And then either in your head or on a calculator, 0.2 times 3 is 0.6. And get used to the idea that area is equivalent to probability when you're talking about a continuous probability distribution, whether it's a uniform distribution, so we're talking about rectangles, or a normal distribution, so we're talking about the area underneath a bell curve from one part to another part. That area that we just found corresponds to probability. So if you write it as a percentage, 0.6 is the same as 60%. So there's a 60% chance that that our waiting time would be between 2 and 5 minutes. So hopefully that makes a lot of sense. So let's go ahead and return to the slides while I erase this. So the shaded area represents waiting times of at least 2 minutes. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. We can easily find the desired probability by using areas. Okay? Well, they say easily. I mean, obviously, it's easy once you practice them, but they make it sound like it's easy in general. But when you are dealing with rectangles, it's not too bad. Okay, so returning to this, here they worked out the same steps that we just did. So I'm not going to talk about it too much, but they got 0.2 times 3, so height times width, and that gave us that area of the rectangle we just found. So 0.6 or 60% probability. Okay, now the standard normal distribution is really going to be our next topic, but I did want to finish up the uniform distribution. So let me skip ahead. I thought we had an example on the uniform distribution here. Oh shoot. Well, I guess we did an example here, and then that's it for what's on the slide. So let me just give you one more quick example of a rectangle, and then we'll go on to the standard normal distribution. Okay, so camera only here. Just going to make up an example. So if we're talking about your homework, I already showed you how to draw a rectangle between 0 and 5. But just for a quick example, let's say that we started with a decimal other than 0. So if we have a uniform distribution or uniformly distributed graph, if we have a uniform distribution between, let's say our graph starts at 1.5 and ends at 4.25. Okay. And then let's say in your homework they asked you to find the probability of being in the region between 2.25, and 3.00. Okay, so find the probability. Find the probability of a data value falling between, I said 2.25, and 3.00. Okay, so on your homework, it's going to be a word problem, but when you're summarizing the word problem, it might be helpful to just write something like what I just did here. When they say uniform distribution, we know it's a rectangle, and a uniform distribution or uniformly distributed between 1.5 and 4.25 means that we draw a rectangle, and our whole graph is going to start at 1.5 and end at 4.25. Okay, and then they want us to find the probability of a data value between 2.25 and 3.00. Okay, so let me go ahead and draw a sketch of this. So 1.5 and 4.25. Okay. 1.5 and 4.25 is what our actual rectangle is going to look like. So just real quick, we have a rectangle that instead of starting at 0, we said it started at 1.5 and it ended at 4.25. And then they asked us to find the probability, which is the same as the area of the rectangle, between 2.25 and 3.00. So our rectangle that we're actually finding the area of is going to start somewhere around here. So that's 2.25. And then it's going to end around here. I'm just doing a sketch, so it's not drawn to scale, but that's fine. So it ends at 3.00, and we're trying to find the area of this region right here. So using the formula, the key is to just draw a picture like this. And then once you've drawn the picture, it should be pretty straightforward to use a formula. So in order to use a formula, we have to use height times width. Okay, so area equals height times width. So in order to find the height, we can do 1 over the range. Okay, so area equals height times width. So over here, height equals 1 over the range. So that's going to be 1 over the maximum minus the minimum. Okay, so that is going to be 1 over 4.25 minus 1.5. So 1 over 4.25 minus 1.5. So at this point, I want to use my calculator. I might be able to do this in my head, but I would prefer to just type in 1 over 4.25 minus 1.5 into my calculator. So let me grab my calculator. Okay, so 4.25 minus 1.5 gives me a height of 1 over 2.75. Okay, so 1 over 2.75. And then if I go ahead and do that division, 1 divided by 2.75 gives me a height as a decimal. So the height that I have here is 0.3636. So the 36 just keeps on repeating, so I put a line over it. Okay, and that's the height. And then the width, when they say width, they actually mean the width of the little rectangle here. So when we were doing the height, we did 1 over the range, and the range is actually the maximum minus the minimum of the big rectangle. So that's how we got that height. And then for the width, we do 3.00, which is the maximum of our little rectangle, minus 2.25, which is the minimum of our little rectangle, the one that we're actually finding the area of. So this right here is going to be our width. So width equals 3.00 minus 2.25. 3.00 minus 2.25, which you might be able to do in your head or using a calculator, gives you a width of 0.75. Okay, and then if we plug all this in to the area formula, area equals height times width. So we've got area equals height, which we said was 0.36, repeating. I'm just going to write 0.36, 0.36. Sorry, excuse me, 0.3636 is what I meant to say, times the width, which we said was 0.75. By the way, you could also have used fractions here if you prefer. But when you have decimals, it's often easier to just write out a bunch of digits. So 0.3636 times 0.75 gives me 0.2727, and it repeats. Okay, so this is an area of 0.27 repeating. So you can either type in 0.363636 on your calculator, or you could write it as a fraction. There are a number of ways of doing it, but this area that we found corresponds to approximately a 27.3% probability. And so this is about 27.3%. Okay, because this is 0.272727, and then when you move the decimal 2 places to the right and round it, it's about a 27.3% chance. Okay, but when you're doing your homework, they will tell you what to round to, and you won't be writing it as a percentage in most cases. I'm just doing that so that we can understand what's going on here. Okay, and that was a pretty good video on uniform distribution, which was the first topic really in 6.1. So I'm thinking, because it's convenient, I'll just make this be part 1 of our video. So I'll call this video uniform distribution from 6.1. And then the next video that I make will be the standard normal distribution. Seems pretty clean to do it that way. So I will see you in the next video on standard normal distribution from the same section. Thank you for watching.